Hello and welcome to Week 10, Part 2 of EGM310, Active Sensors. In this lesson, we will discuss active remote sensing, that is, sensors that apply their own source of electromagnetic radiation. Recall that remote sensing typically involves measuring electromagnetic radiation. In order to measure electromagnetic radiation, we need some kind of source of electromagnetic radiation. This can be the sun, as it is for most forms of optical remote sensing. This can also be the object itself. Remember that if something has a temperature above 0 Kelvin, or absolute zero, it will emit electromagnetic radiation that can be measured. When we record electromagnetic radiation that is reflected by the sun or emitted by the object itself, it is called passive remote sensing, and we'll talk more about these examples in the next lesson. If the source of electromagnetic radiation is the sensor itself, however, it is what is known as active remote sensing. You have probably all heard of radar before. It originally stood for radio detection and ranging, though it has since entered the English language as an actual word. Radar involves making observations in the radio or microwave portion of the electromagnetic spectrum. We're going to focus on microwaves here, which is the portion of the electromagnetic spectrum corresponding to wavelengths between about 1 millimeter to 1 meter in length. The original purpose of radar was to detect objects and find out how far away they are and how fast they were moving. That is, find the range to the object. To do this, we first send out a signal like the one shown here, and then we measure how long it takes for the signal to reflect off of the object and come back to our receiver. This gives us the travel time to the object. If we know the speed of the signal, which we usually do because it's the speed of light, then we know how far away the object is. It's just the speed times the time it takes for the signal to come back, delta t, divided by 2. In doing this, we can also measure the signal strength. How much energy is reflected back to our receiver. This gives us some information about the object, perhaps how big it is or the properties of the surface. Using a polarized signal, we can find out even more about the object. We can also measure the phase or partial wavelength of the signal that returns. This can tell us even more about the properties of the object as well as more about the distance. The frequency of the returning signal can also tell us something about how fast the object is moving. Recall that the atmosphere is largely transparent in the microwave portion of the spectrum, which means that we can make observations regardless of the time of day or time of year. This is especially useful in polar regions, and we can even make observations that are somewhat independent of the weather. One widely used application of radar in remote sensing is what is known as altimeters. As the name might suggest, an altimeter measures the distance between the satellite and the Earth's surface, which tells us about the altitude of the surface. Radar altimeters can achieve very high accuracy, down to as little as 3 centimeters difference, which is rather impressive given that we're making these measurements from about 700 kilometers away. The large footprint of the altimeter signal, however, means that we're limited to measuring the height of large, relatively flat surfaces, such as the ocean, or the interior of the ice sheets. Another widely used application of radar is what's known as synthetic aperture radar, or SAR. It turns out that the resolution of a radar, that is, the ability to differentiate between different objects, mostly depends on the size of the receiving antenna and the wavelength of the signal. This means that for a commonly used radar signal, known as C-band, with a wavelength of about 5 centimeters, we would need an antenna that was nearly 4,250 meters long in order to have a spatial resolution of 10 meters. Fortunately, we have a bit of a workaround. The way that a SAR system sends and receives signals is designed to imitate a much larger antenna. The details of this are outside of the scope of this course, but I have included some links below that go into a bit more detail about this. SAR is probably the most common form of microwave remote sensing used, with a wide range of applications. The images that we get from a SAR sensor are quite a bit different than the kind of images you might be used to. One example shown here on the slide. Looking at this, you might be able to guess that this is an image of some mountains somewhere, but I imagine that picking out different features might be a challenge. This is because the characteristics of this signal that we receive depend very heavily on the wavelength of the signal and its polarity, the surface characteristics, for example, its structure or moisture content, and the geometry of the surface. Mountainsides oriented toward the sensor, such as what we see here, will look quite a bit different than mountainsides that are oriented away from the sensor, such as the examples that you can see on the other side of these bright lines. SAR is a very powerful tool, but it does take some getting used to. Depending on the properties of the surface and the wavelength, a SAR signal will actually measure beneath the surface. This means that by using signals with different wavelengths, we can get information about different layers within the surface. For example, we can learn about the structure of forests. We can also track and measure surface moisture. When combined with the fact that clouds are mostly transparent to SAR signals, this makes SAR a particularly potent tool for monitoring and studying floods, as shown in the example here. We can also use SAR to measure surface topography and surface motion using a technique called interferometric SAR or Insar. This can help us study things like ground subsidence in areas where groundwater is being depleted, as shown in the figure here on the left, or areas where volcanic activity may be causing the ground to uplift by very small amounts, as shown in the figure on the right here. So the highest elevation difference that we can see here, this red color, corresponds to about 25 millimeters difference. And again, we're making this measurement from space. This is a very powerful, useful tool. Similar to radar, LiDAR stands for light detection and ranging. Rather than using radio signals, we use lasers in visible or infrared wavelengths. LiDAR works on a similar principle to radar. The sensor sends out a signal, waits for it to return, and measures the travel time and signal properties, which tells us information about the surface that we're observing. Depending on the application, we may use a laser with a wavelength corresponding to visible green light, approximately 600 nanometers, or up to around 1,000 nanometers in the near-infrared portion of the electromagnetic spectrum. Depending on the wavelength used, LiDAR can give us information about topography. A common application of LiDAR is used for mapping elevations, as the elevation data returned are both dense and highly accurate. It can also tell us about vegetation structure. Similar to radar, the sensor gets returns from different parts or portions of vegetation cover and can even be used to remove vegetation from elevation data. If you remember to the example I showed last week from Owata Phoenix in Mexico, this is how archaeologists working in southern Mexico were able to map monuments and cities through dense forest cover. With lower wavelengths, such as green light, LiDAR can even be used to map bathymetry in shallow areas. The example profile shown here is from the ISAT-2 satellite, which uses a green laser to map elevation across the globe. In this lesson, we have learned about how we use active sensors to produce a signal and then measure the response of an object. One type of active sensor, called an altimeter, can be used to map surface heights very precisely, at least on relatively flat surfaces. Imaging sensors, such as synthetic aperture radars, provide an image of an area, though the image might look quite different to what we're used to. Depending on the signal wavelength, active sensors can be mostly weather independent and can even make observations when there's no sunlight to reflect, because the sensor is providing its own source of electromagnetic radiation. Finally, we've seen that active sensors can be used for many different applications. Once again, you can read more about the concepts that we've covered in this lesson in the textbooks, either Chapter 6 of Lillesand, Kiefer, and Chipman, or Chapters 7 and 8 of Campbell and Wynne. You can also read further on the Natural Resources Canada remote sensing tutorials. Finally, I've linked to 2 videos here that go into more detail about synthetic aperture radar and LiDAR respectively. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!